My name is Dan McGeehee, the director of the National Advanced Driving Simulator here at the University of Iowa. I'm also on the faculty in Industrial and Systems Engineering. We're delighted to have you here today in this webinar that will talk about a really important element as the progression of automated driving moves forward, especially from those areas that have perfect roadways like they do in Silicon Valley and Arizona, where perfect paint, perfect roads, and perfect weather are the norm. This project really concentrates on a roadway infrastructure that is not the norm, those places that don't have paint, gravel roads, 4 seasons of winter, and so forth. So this project really opens up another important element of becoming the reality for automated driving systems. Before we get started with my colleagues, I'd like to introduce our team, as well as some of the sponsors that we have here. You'll hear first from Omar Ahmad, the project manager for the ADS for Rural America project. We'll also have other colleagues join us along the way today, but I wanted to also talk about the great work that Steve Cable is doing in the data management side of things. Cher Carney, who is the research lead, Alec Lavelle, who is a safety driver and the data request manager, Sherry Rowe, who is our head of our safety and logistics, Christine Rogentine from communications, and Greg Wagner, who is the head of our instrumentation engineering group here at the National Advanced Driving Simulator. Most importantly, it's very important to acknowledge our sponsors. First, the US DOT, who's the primary sponsor of this, the Federal Transit Administration, who is putting together the logistics from the government side of this project, the Iowa DOT, Autonomous Stuff, and Manley Communications are all critical to the overall operation of this project. It's really a great team. The personality chemistries are super. With that, I'm now going to introduce you to my colleague, Omar Ahmad, who's the project manager of the ADS for Rural America and also the deputy director here at the National Advanced Driving Simulator. Thank you, Omar.
Thank you, Dan, and thank you to all the attendees for joining us today. I'm going to start us off, and first of all, I'll give you a bit of a layout for how we'll do this today. So I'll start us off with an overview of the project and some of the initial lessons learned, and then I'll hand it over to my colleagues who will describe our approach to safety and the development of the safety management plan, as well as how we've applied that to safety monitoring and testing with the ADS vehicle on roadways. So the ADS for Rural America project is part of the demonstration grant program from the US DOT. And our project is focused on the ability of automated vehicles to drive themselves on rural roadways. And this is very important because in the recent testing that's been done, it's mostly taken place in urban areas and on interstates. And the reason why we want to look at rural roadways is because while a smaller segment of the population lives in rural areas, half of all traffic fatalities occur on the same rural roadways. So if automated vehicles are going to realize their promise of improving safety for everybody, they need to do so on all types of roadways, including rural areas. Another important aspect of looking at rural roadways is the communities that are connected by those roadways and the people that live within them. So the US has an aging population, and many older people live in rural areas where they have little or essentially no access to public transportation. And as people age, being able to move around, being able to be mobile is equivalent to freedom and maintaining independence. And what we're also seeing is a regionalization of services. So services like healthcare are largely being provided by regional centers that are typically located in urban areas. So automated vehicles can potentially be a great way to connect mobility impaired populations that are in rural areas to each other, but also to the urban centers that they need to get to those services. Our project is primarily about providing data on the performance of the automated vehicle on rural roadways, as well as data from trust and perception of older folks, trust and perception of older folks and how they view automated vehicles. So I'll now briefly cover a few of the lessons learned from the initial phases of testing. And our project is organized into 6 phases of data collection. And today I'll be talking about some of the lessons learned from the first phase, which was completed back at the end of 2021. So one of the things that's supremely important is anytime you have a team of people that are utilizing an automated vehicle to do testing on open roadways, it's so important to have clearly defined roles. And in our case, we decided that we would not only need a safety driver, a dedicated safety driver, but also a co-pilot, as well as remote monitoring. And my colleagues will describe the roles in a little bit more detail in the latter parts of this webinar. It's also very important anytime you have an automated vehicle or an ADS vehicle, typically there's going to be an entity that provided that vehicle to you. And in our case, we have a technology provider in autonomous stuff. And we cannot stress the importance of regular and constant communication between the technology provider and the entity like us that's utilizing that vehicle to do testing. And as great as a technology provider can be in helping you solve problems with that pop up with an automated vehicle, and there will be problems with any of these vehicles, you need to have on-site staff that are trained to troubleshoot some of the simpler issues. So it's important to not just see the automated vehicle as this entity that is supposed to be perfect and will never break down. You have to expect that problems will happen, and you have to have some training on how to troubleshoot and diagnose those problems. Automated vehicles are nowhere close to being perfect, and they have a lot of issues. And certainly one of the issues that we encountered was the max speed. So our vehicle initially had a maximum speed of 50 miles an hour, and in fact, with a lot of the publicly available technology automation stacks, max speed is an issue. But this really changed the way in which we had to operate the vehicle on open roadways, on highways, and on interstates. And we had to take additional safety measures in order to be operating in an environment where our vehicle was traveling slower than the average speed of the vehicles on that roadway. Automated vehicles also drive in a very specific way. They're programmed to drive in a specific way, and they tend to drive the same way regardless of what type of roadway they're on. So for instance, when you get to a gravel roadway, which may be narrower, the automated vehicle is still going to want to drive on the right edge of the gravel roadway. And whereas a human being, when we drive gravel roadways in Iowa, you're typically the only vehicle on that roadway, and you drive in the center of the road, and then you move over as you approach an oncoming vehicle, and then move back to the center. So this is not something that automated vehicles do, not yet anyway. Also, automated vehicles may be very slow to start from a stop position. And certainly that was the case with our vehicle when it would start from a stop position, whether it was at an intersection or at a railroad crossing. It was slow to start, and sometimes it would be hesitant. It would start and maybe stop and then start again. And this can be very annoying for the human drivers that are behind an automated vehicle. So this is certainly something to keep in mind. And then automated vehicles are, as I've mentioned a couple of times before, they're very complicated, and there's a lot of computing equipment that's being utilized to make these vehicles work. And just like your desktop PC that occasionally requires restarting or rebooting, an automated vehicle also requires restarting and rebooting. And this is something that can take minutes, several minutes, in order to get the vehicle back up and running if there's an issue. Finally, we experience issues with weather. So automated vehicles, again, the behavior does not change typically when an automated vehicle is in bad weather. So the vehicle is going to drive the same speed regardless of the weather conditions or the roadway conditions, and it will follow the same path regardless of whether the lane is clear or whether it has snow on it. And this can be very good, and this can be very challenging. So in our case, what we experienced was that as we experienced snowfall in Iowa and we drove the vehicle still wanted to stay perfectly in the center of the lane, even though the path that was created by the vehicles in front of us may have been biased more towards the center of the lane. Similarly, ice was an issue. So as ice formed on the sensors, the vehicle was not able to see other objects. And so on the top right of the screen, you're seeing an image, a LiDAR image from when the sensor is operating as we expect, and it can see everything in front of it. And then on the bottom right, you're seeing an image from a LiDAR sensor that has ice accumulation, such as what you see on the bottom left here. And in that case, the sensor is essentially blind. And what was really striking to us was that that the automation software did not really know that the sensor wasn't operating as expected. From its perspective, there were no cars in front of us. It didn't realize that the reason why we couldn't see anything was because there was ice covering the sensor. So those were just a few of the issues that we encountered. And now I'm going to turn it over to my colleague, Cher Carney, who's going to talk about the safety management plan.
Thanks, Omar. So safety is incredibly important in everything that we do at NADS. The safety of our participants and other road users and our staff is really our main focus. So for this project, we developed a safety management plan that's made up of 3 different parts. It includes a description of the safety team that outlines each person's role, the training requirements for the safety team, and the procedures that we have put in place for ensuring safety. So I'm just going to touch briefly on each of these parts of the plan. Next slide. So the ADS for Rural America Safety Team is made up of staff members at NADS, and these staff members have over 50 years of combined experience working in the areas of vehicle automation and conducting research. As Omar mentioned, the key to our safety team is that it is comprised of several individuals who have really specific, well-defined roles. So the role of the safety driver is to safely operate the vehicle. Basically, they're expected to monitor the road and the behavior of the vehicle at all times, to take over from the ADS whenever they feel it's appropriate, to take control of the vehicle in case of system disengagement, and to drive the vehicle whenever it's outside of its ODD or operational design domain. The co-pilot sits in the front passenger seat, and they're responsible for monitoring the proper operation of both the vehicle and the automation, and communicating with the safety driver to help enhance their situational awareness. So in essence, they're really a second set of eyes and ears for the driver. They're also responsible for placing flags in the data to identify any specific locations or any interactions that happen that we might want to go back and review. We have research and data collection staff that sit in the rear of the shuttle with the participants, and their main role is to ensure the safety and comfort of them, to go over instructions and to consent them, and then to collect the biometric and questionnaire data. We have vehicle instrumentation and maintenance staff that are responsible for the health of the vehicle and all the equipment. They inform the operators of any changes that are made to the vehicle that might impact the ODD, and then they complete the inspections and document any issues and how those issues get addressed. And then finally, we have a remote vehicle monitor who has access to live video outside of the vehicle, and they provide assistance to the vehicle operators in case there's any sort of emergency situation. They would also be the one who would contact the rider's emergency contact and initiate the crisis communication phone tree if necessary. They also document any specific interactions or issues that we think we need to go back and review as well. Next slide. So our safety management plan also describes the extensive training that our team goes through. The entire safety team is trained on both the basic vehicle systems as well as all of the automated driving systems. The basic vehicle systems training is done here on campus with the help of the University of Iowa Fleet Services. With them, we complete both classroom and hands-on training that includes things like the emergency procedures, pre and post-trip vehicle inspections, wheelchair lift operation and wheelchair securement, and then basic vehicle operation and maneuvers. Throughout the project, we review all of these skills, we practice them, and especially those that we might not commonly use or that we maybe didn't experience during training, like driving on snow. Next slide. Our ADS training is done with the help of our technology partner, and it includes understanding the different types of sensors on the vehicle, their role in the automation, and the functionality and limitations that are associated with each of these. Additional training includes performing automation and data collection startup procedures, practice engaging and disengaging the automation and responding to any unexpected disengagements that might happen, and then understanding the in-vehicle displays and all of the information presented on them. The on-road training exposes the safety team to increasingly complex driving environments until the safety driver and the co-pilot are comfortable driving the entire ADS for Rural America route. Our training occurs at the start of the project, and it is performed again before each of the phases as the system and the vehicle are modified or upgraded. Next slide. And then finally, we have procedures in place for many different types of emergency situations, including fire, medical, crashes, and weather. These approaches were developed following the University of Iowa's own fleet service guidelines, as well as guidance from other rural transit authorities that we've reached out to. In the case of weather, the decision to cancel a drive is made by our research team, and it's led by the safety drivers and our project manager. The safety of the vehicle and everyone involved is really our priority. So we'll cancel a data collection drive if there's severe weather warnings or advisories that are on or near our route. But we may also complete a drive and choose not to have subjects on board. For example, in phase 2, we did 2 drives that did not have subjects on board, and these were due to winter weather advisories. We didn't want riders to have to travel to the pickup locations, but also the vehicle had not been driven in snow or ice yet, and the ADS safety team wanted to see how the vehicle and the sensors would operate. So I've just touched briefly on some of the different parts of the plan. If you have specific questions or you'd like a copy, I think you can reach out to either Christine or I via email, and we should be able to get that to you. Next, I think Sherry is going to talk a little bit more about the testing procedures and vehicle monitoring.
Thank you, Cher. As Cher mentioned, I'm going to provide an overview of what our safety team has developed to ensure safety during testing and data collection. I'm going to highlight some of the procedures, the interfaces, and the testing process. As you can see on this screen, it's a view inside of the transit. You'll see 2 interfaces, one for the safety driver and one for the co-pilot. The information that is presented has been thought out and tested by our safety team to maximize safety and usability, as well as minimize any kind of glare. The driver interface is designed for quick glances and is positioned near the driver's side mirror to allow the driver the ability to glance at when scanning the environment like a mirror check, thus not interfering with their ability to safely operate the vehicle. Since the co-pilot's responsibilities differ, the co-pilot's interface is positioned closer and is adjustable so that co-pilot can interact with the interface during the drive. Next slide. The safety driver's responsibility is to operate the vehicle. Our safety drivers have been trained to drive with both hands on the steering wheel, regardless of the automation status. The right hand stays on the wheel near the engagement and disengagement buttons. When in automation, the safety driver will keep their right foot near the pedals. Our preferred method of disengagement is to press the disengagement button. However, when necessary, turning the steering wheel, pressing the accelerator or brake pedal may be a more suitable and safer method. For example, if the vehicle steers towards a lane boundary, the more natural response would be to steer to disengage the automation. The image on the right is our safety driver interface. This interface provides situational awareness to the safety driver about the automation status and the environment. Before engaging automation, the safety driver will glance to the top part of the display to verify that the route and the planned path are available. Additional glances are made when approaching vehicles or pedestrians to verify the automation system sees the objects. Since the co-pilot's main responsibility is to monitor the operation of both the vehicle and the automation, it builds upon the safety driver's display. But unlike the safety driver, the co-pilot glances from the road to this interface continuously throughout the entire drive. This allows them the opportunity to verify that the automation is correctly identifying the route, the planned path, and perceiving the objects in the environment accurately and in a timely manner. If the sensors aren't, the co-pilot will communicate that information to the driver. The co-pilot also communicates any changes with weather or road conditions and sets parameters for the ADS drive recordings, start and stops recordings, and places markers or flags in the data. This is a video of the co-pilot interface during a drive. I'd like to draw your attention to the bottom left. As the video progresses, you will notice the system perceives the vehicle ahead of the transit, as it appears as a green box. If you want to see the video of the vehicle, please see the upper left small camera view. You may also notice that the automation transit maintains a safe distance from the vehicle ahead while navigating the corner. You may be wondering why the rear view camera is larger in that upper left quadrant. Since our co-pilots see out the windshield, the ability to see behind us is more accessible with this view. We can go to the next slide. For added safety, Cher mentioned we have a remote monitoring person. We have this person so that they can see what's happening real time. They use this screen to communicate with emergency services and or riders' emergency contacts, as well as identify any potential issues with cameras, the recordings. They can also see inside of the vehicle with the passenger central display, which is shown in the upper left-hand corner. Next slide. As we've mentioned, ADS project uses a complex route. It's 45 miles long and includes urban roads, controlled access highways, highways and ramps, unmarked roads, gravel, and parking lots. Our approach to handling this complexity was to break it into phases, allowing us to focus on different automation updates over time. Each phase begins with our team working with our technology provider to test, modify, and validate the updates to the automated features. The testing involves simulations, closed course testing, and remote sessions with our team. When the time comes to validate, the technology partner comes to our site and works directly with our safety drivers, doing tests on both our ADS loop and our testing loop near our facility. During these drives, we identified challenges that may not have been seen during simulations or closed course testings, and further fine-tune any automation performance issues for the current phase as well as the entire route. The safety drivers then take over and they drive repeatedly, focusing on the new phase multiple times. When that becomes comfortable and familiar, the full routes are completed. During full route testing, the drivers identify and map out targeted locations for the automation to be engaged and disengaged. The final step prior to data collection includes driving full data collection routes with internal employees riding as passengers. These drives start at our ADS predetermined locations at different times of the day. These allow us to identify any safety concerns or data issues related to location or the time of day. Next slide. Our daily schedule starts with pre-safety checks and startup at our facility. These safety checks include standard transit checks as well as automated feature checks. The researcher takes responsibility for the passenger compartment. Once the checks are complete, the team completes a safety test drive on our NADS loop to verify that the safe operation of the vehicle and its automated features. This route is useful for us because it allows us to experience speed changes, traffic lights, stop signs, and turns. During this drive, the co-pilot monitors while the driver engages and disengages automation using each of the 4 disengagement methods. Our safety during a data collection drive: 2 subjects ride and are picked up at predetermined locations. They do board individually so that we can provide them individual assistance, verify emergency contact information, and maintain their confidentiality. Everyone on board wears a seatbelt when the vehicle is in motion. During the route, the transit makes predetermined stops for data collection purposes. However, for safety reasons, passengers do not enter or exit. The stop allows our safety driver and co-pilot a short break to check recordings, cameras, and sensors, or to take a quick drink of water, or even to stretch out their arms because they're getting stiff. After the drive, everyone exits, again individually. The team then returns to NADS for a series of post-drive checks and a debriefing meeting. This debriefing meeting is important in that the current safety team provides a summary to the rest of the team, highlighting the performance of the automation, encounters with vulnerable road users. We address subjects' questions or concerns and anything else of importance. Next slide.
Thank you, Sherry. I just want to kind of cover what we've talked about in the last few minutes. So in terms of lessons learned, we talked about having very clearly defined roles for everyone on the team, and communication between the team members, communication between the team here and the technology provider is so essential. And then we cannot overstress the importance of training, and not just training at the beginning of the project, but retraining between phases to make sure that everyone is on board and has the same mental model of the capabilities of the automation, which are changing and mostly improving over time, but every now and then the capabilities may also take a half a step back. And this is a very common thing with any type of an endeavor in which you're trying to do things that have potentially never been done before. And that really highlights the importance of testing and retesting. In our case, a clear and detailed safety management plan was so essential, and it included information on all of what we've described to you before, but really calling out the team roles, the protocol, the training, how to deal with external folks that are riding in the vehicle with us, the emergency procedures, the testing and monitoring protocols, and then the inspections and the reports, and the debriefings that take place after each drive. We encourage you to contact us if you would like more information, and we'd be happy to share a copy of our safety management plan if that's of interest. And with that, we thank you very much for spending some time with us, and we'd be happy to take any questions.
Yep, so we had some questions that came in from the registration form. And if anyone else has any questions while we talk, please feel free to put those into the Q&A, and we're happy to answer those. So one of the questions that came in was, you talked about this a little bit, Omar, but if there's anything else you want to say about this, what are the biggest challenges from phase 2 of the project, and how did we overcome them?
Yeah, so certainly, we covered some of the challenges related to weather. Weather really was something that required us to adjust our plans, and really think about when it would be safe to operate the vehicle with participants, when it would be potentially okay to operate without participants, and when it was just plain unsafe to operate the vehicle. And this was a challenge for us because, on the one hand, we really want to know how well or what are the challenges that an automated vehicle encounters when it's driving in bad weather, but we still have to balance that against safety, and safety is paramount. And so certainly we were able to learn a few things that I think related to sensor performance and degradation of it. These were important lessons. The key thing here is that we work together as a team, and then the constant communication between us and the technology provider, Autonomous Stuff, was so central to when there was a problem, to being able to sort of discuss it and overcome it quickly.
Another question that came in: how has law enforcement and public safety been engaged throughout the project?
I can answer that one. So before the project even started, we had several meetings with stakeholders throughout the different communities that we're traveling through. And this included people from law enforcement agencies. We wanted to make sure that we had engagement from the very beginning of the project. And we also reached out to the University of Iowa's risk management, and everything that we've done has been approved by them, as well as our internal review board here at the university.
Okay, great. Another question: could you mention analysis applications that are being used to analyze the data?
Sure, I'll go ahead and jump in here. So really, as Omar has kind of talked about, the focus of this project was more necessarily on the collection of the data, and not necessarily do in-depth data analysis. So that being said, although there's definitely room for that analysis to be done. So that being said, we are doing some lower level analysis that kind of takes a look at the automation performance and create visualizations and things like that. Those definitely kind of fall into three different areas. So for things like for immediate review, ROSBAG data which is the way that we're recording, is played back through bench systems, which show the same interfaces that you would see in the vehicle. So for the safety driver and the co-pilot. So those share a similar track. Those are all software that is developed in-house. That being said, we also use off-the-shelf ROS tools like RViz, or playing back recorded data through Apollo's DreamView interface. We've also written a lot of things that are, again, using kind of off-the-shelf open source modules like ROSBAG to create things like KML maps or summary data from each drive. And then we also have people who are using Python to do the actual data ingestion from the ROSBAG recorded files to then ingest into the main source of distribution that we'll have for the data, which is going to be on our upcoming data access site that will be coming out shortly. So that Python data will feed into on the data site, feed into the playground, what we're calling the playground, which will kind of give researchers kind of easy access to correlated data within the data set, or to get in touch with our data managers here to request. You can even go down to request the raw recordings of the data from the vehicle, which may kind of come along with a data usage agreement. But that kind of explains a little bit of it. And if you have any questions, feel free to reach out directly.
Thanks, Steve. Sherry, this is probably one for you. What is it like driving as a safety driver versus driving a regular vehicle?
Well, it's very different. I can definitely say that it's the there's different levels of stress, I would say, with being a safety driver versus just driving normally. And when you add passengers on board, I think that stress goes up a little bit more. I think the big thing for me that I've noticed is that I get a little stiff on the route. That's why when we stop, it's really important for me to like stretch out my shoulders. And I think it's because, you know, we're placing our hands on the wheel, but really not interacting with the wheel. So we're really like, you know, lightly holding them over the wheel in the air. So it's putting kind of, you know, tensing up muscles that you wouldn't normally tense up maybe when you're driving. And the level of, I mean, we're always really engaged in the road and watching, but I think it's even more intense when you push that automation engagement button.
Yeah. Okay, cool. Let's see. So we have a couple in the Q&A. Could you expand on the types of flags that are being applied to the data by the co-pilot and whether those are, quote, visible to other researchers and the public?
Yeah, so we are placing flags for 3 different reasons, really. The first is anytime there's any type of disengagement of the system. So this could be voluntary disengagement. For example, if we're entering a town in which the speed limit decreases and the system doesn't recognize it, the driver may voluntarily take the system out of automation. We also flag for forced takeovers. So let's say the system disengages itself for some reason, and the driver is forced to take over. Those get flagged as well. The second type of flag is for any voluntary or vulnerable road user that we encounter. So along our route, we see a lot of horse and buggies, we see ATVs on the side of the road, pedestrians, bicyclists, any of those things get flagged, and we identify whether the vehicle is in automated mode or in being driven manually at that point. And then our flags are also placed for any safety critical events that happen. This has been rare so far. We're in phase 2 and we've only had 2 safety critical events. So yeah, those are the flags that are put in there. As far as whether or not the public and it's visible to them and researchers, those are in the data. So anybody who had access to the data would be able to see them. So yeah, hopefully that answers that part of the question.
Yeah, I think so. Another question in the Q&A, you mentioned that automated driving on gravel roads stays on the right-hand side as if it were following a lane on a marked paved surface. In the absence of lane markings on gravel roads, what do the sensors use to track that right-hand lane?
I can take that one. So we're driving a 47-mile route, and at the beginning of the project, this route was mapped in high definition by our technology partner, Manley Communications. And so what this map does is it's an extremely accurate map of the route, the road, the lane markings, and key signs. And so when the sensors are not able to see lane markings, or when there are no lane markings to begin with, because we do have both paved and unpaved roads on our route that have no lane markings, then the map serves as a great resource for the vehicle to be able to essentially see where it's at. And it's more than the map. There's a lot of equipment involved in making this happen. So you have to have the map, you have to have the right equipment on board that allows you to essentially position and localize yourself on the map. And this equipment consists of GPS, and also it utilizes the state's RTK network that allows for that precise positioning, because regular GPS that we have in our phones and our vehicles is not that accurate. I mean, you can probably localize yourself to somewhere on the road, but you certainly couldn't place yourself exactly in your lane. And there are new technologies out there that enable vehicles to do that. So all of this really works together to be able for the vehicle to essentially place itself in the correct place on the roadway.
Okay, great. Another question that just came in: when will the data be available to other researchers and the public?
Yep, we've been collecting data for phase 1 and phase 2. We're still in the process of completing the interfaces that'll basically allow users to view the data and to work with it. So we anticipate that we'll be able to share the data in the second or third quarter of this year. The data will be shared via a data portal, and access to the data portal will be available through our website. And Christine will be able to place a link to the ADS for Rural America website. And you can, when you go to that website, you can sign up for our newsletter now. And then the newsletter will also provide you updates on when access to the data portal will be open for everybody.
I just put that link in there again. And that's all the questions that we have that came in. Unless I'm missing anything, feel free to type one in quick while we're wrapping up here. But as Omar said, you can subscribe to our newsletter on our website. We only email you about quarterly, so I promise we won't bombard you with emails. We are planning on holding these webinars about quarterly throughout the duration of the project, so through about next summer. So you can see some updates from us from our newsletter and on our website. You can also follow us for project updates on Facebook, Twitter, or LinkedIn. Just search for National Advanced Driving Simulator. A recorded version of this webinar will be available on our website if you want to share it with any of your other colleagues. And yeah, no other questions have come in, so I think we can go ahead and end the webinar. So thanks again, everyone, for joining us, and have a great day. Bye.